Hey, Becomers, Missy here. So we're going to talk about mechanisms today. And you have seen mechanisms once before. We talked about them slightly when we were first talking about rate laws and differential rate laws and how we could write them. And briefly in your text, it talks about how if we can see the elementary steps or the individual small reactions that are happening to go from our reactants to our products, then we can figure out if we're told which one's slow, that one can help us determine the overall rate of our reaction, because that slow reaction takes the most time. Therefore, that one really determines how everything behaves and who takes longer and who doesn't. So we're going to dive into that a little bit more. And you can think of mechanisms like a puzzle. Okay, so a puzzle of putting our parts together to get from the reactants that we're starting with to our products that we want to get to. So a few definitions. A mechanism is the sequence of elementary steps by which a reaction proceeds. The elementary step is just the little reaction that we're looking at to help us move forward in our reaction. We have intermediates, which is a molecule that's made in one elementary step and then used in another. So it's a product in one and a reactant, usually in the one right afterwards, although it doesn't have to be, but typically it is. And then remember, a catalyst, when we're looking at reactions, a catalyst is put in as a reactant and then comes out as a product, but it doesn't get used up. It just provides that alternative pathway to help our reaction happen, lowers that activation energy, so that way the reaction can actually happen in a timely manner. So here we have, I wonder if my night light's still on. Yep, there you go. This makes it better for you guys. So for an example, if I have nitrogen dioxide plus carbon monoxide makes nitrogen monoxide and carbon dioxide. Okay, so this is my reaction. And a mechanism that is proposed for this reaction to happen is the first elementary step. I have a nitrogen dioxide collides with another nitrogen dioxide to make nitrogen monoxide and nitrogen trioxide. And then that nitrogen trioxide reacts with my carbon monoxide to make my nitrogen dioxide. Oops, this should be NO. Nope, that's right. Makes a nitrogen dioxide and a carbon dioxide. So I want to know, is this a possible mechanism or not? So what we need to do is we need to see if adding both of these together, if that then gets us back to our original reaction by canceling out things that are the same on both sides. So if I have NO2 and NO2, so I have NO2, which you guys can't see. Oh, I'd like to zoom in. There we go. Okay, so I have NO2 plus NO2. I'm going to put all my reactants on the reactant side, plus NO3 plus CO makes NO, NO3, NO2, and CO2. So I'm going to cross off things that are the same on both sides. So NO2, NO2, cancel out. NO2, not another one, so that stays. NO3, NO3, that goes away. CO, nothing over here. Carbon dioxide, nothing over here. So then I rewrite what I have left. NO2 plus CO makes NO plus CO2. And you might have not had to have written this step down. That's fine. I'm just showing to illustrate everything. So we can see that when it's all said and done, I have things that no longer exist, right? I have nitrogen dioxide I've used, and then it's gotten created, right, as I've used it up and made it so that it comes out to being null. Same thing with my nitrogen trioxide. So overall, this proposed mechanism is an option, right? It does give us our desired products given the starting of the reactants that we have. So we'd say yeah, it's possible. It could work. A couple of notes here. Lots of times then you're asked, do you have a catalyst? Do you have an intermediate? So if we look at our reactants, we have NO2 as our reactants, right? One of our reactants. And then although it does come out as a product in the end here, we also know that it's one of our reactants. So it means we don't have a catalyst here. What we do have, though, is we make NO3 here, and then we subsequently use it up here. So NO3 is an intermediate. So it's usually some awkward form. It's at a higher energy, and it gets made, but then we right away go ahead and react it with something else and change it and move it into something else. Okay, so this is an intermediate. Now, given elementary steps of my mechanism, sometimes if I'm told which one is the slow step, I can then write my rate law based off that information. So our rate determining step, or RDS, is the slow step. So it's the step of my reaction that takes way more time, which takes the majority of the time, therefore is the one that ends up being my rate of my reaction. So then we can use the coefficients on the reactants in that slow step of the mechanism to write our rate law. So then we can say that the rate of the reaction is the rate determining step. So what if looking at my reaction from above and my proposed mechanism, what would the rate law be if the first elementary step is the slower reaction? So what if this reaction took 60 seconds to happen and this one take 0.001 seconds to happen? Well, if I want to know the overall amount of time that my reaction took, well, 60.001 seconds, which is basically 60 seconds. So that means that this reaction here is essentially determining how fast my reaction goes. So that means that this reaction is my rate determining step or my slow step. So you'll get it listed as slow versus like fast is usually just what they say after them. Sometimes you get data, but usually just says slow or fast. So if this is my slow reaction, that means that my elementary step 1 is the one that's going to determine the rate, and that's how I can then write my rate law. So that means that my rate, remember rate is equal to K times my reactants, and in here I have NO2 and CO. Okay. My rate determining step only has nitrogen dioxide in it. It doesn't have carbon monoxide. So that means carbon monoxide its concentration doesn't impact the rate of my reaction. So instead, I only have to worry about my nitrogen dioxide. So I look at my slow step and I say, well, in my slow step here, my only reactants are 2 nitrogen dioxide. So really, my rate for my slow step, my first step, looking at my reactants, I have K times my first nitrogen dioxide and my second nitrogen dioxide, both of which have coefficients of 1. Okay? Or I can simplify this more. Something times itself is that squared. So I could say, furthermore, the rate of my reaction is K times my NO squared, right? Because I could rewrite this as 2 NO2, right? Because I could combine them because they're like terms. So this is the rate of my overall reaction. So my reaction is second order. And then from here, I could then look at, well, what's my second order integrated rate law? I could get time data, figure out reactions, right? We can do all of that once we know the order of our reaction. So think of these like a puzzle. The other thing that you could get and that you will get is you'll be given, like, if I know my order, okay, so if I say it's second order in reaction A, first order in reaction B, which of these mechanisms could be viable, right? Then I would start to look at my elementary steps and say, well, if this is my slow step, that doesn't give me a rate law that matches the actual rate law, so this cannot be a proposed mechanism. And that's a way for us to start to figure out what's happening, even though we can't actually see it happening.